In the previous lecture, we have started to discuss the conservation laws and symmetry. In the first introductory lecture on conservation laws and symmetry, you have seen that every conservation law is corresponding to some symmetry or invariance. So I have mentioned some of the important facts which you have studied in the previous lecture. So just as a revision, I have mentioned here the symmetry and invariance and corresponding to that symmetry which conservation law is followed, I have mentioned here. All these things you have seen in the previous lecture. When the symmetry is actually approximate symmetry of up and down quarks, then you have seen that this leads to a conservation, an approximate conservation principle of isospin, and the invariance of space leads to the conservation principle of linear momentum, and the invariance of time actually leads the principle of conservation of energy. Similarly, you have seen that the invariance of rotation leads a conservation principle which is called conservation of angular momentum. And symmetry under reflection in space, that is when the origin is just reflected, that is the position vector r becomes minus r, then that leads the conservation principle of parity. And similarly, you have seen that symmetry under exchange of particle and antiparticle leads to the conservation principle of charge conjugation. So these were some of the important informations which we have seen in the previous lecture. But these things we have seen only just as an information, not any mathematical calculation or not any rigorous explanation of it. In fact, this lecture is in the continuation of the first lecture, and you will see the explanation of these facts, that is how symmetry leads a conservation principle, we will see in this lecture. Okay. So let us start to know what is symmetry and conservation laws. Actually, this is dealt in terms of a theorem which is called Noether's theorem. Actually, Noether was a famous mathematician who invented a symmetry theorem, and that theorem actually implies that with every symmetry or invariance, definitely a conservation principle will be associated. In fact, the root of all symmetry principle lies in the assumption that it is impossible to observe certain basic quantities, and the quantities which cannot be observed, that is those are actually called non-observable. You know, you have studied the observable in quantum mechanics. The measurable quantities are called observables, but if we cannot measure or we are not able to measure any physical quantity, that quantity will be called a non-observable. Actually, the root cause of this symmetry principle lies in non-observable. It means you can say that with every non-observable there will be a symmetry, and this fact will be explained in this lecture. So let us start to understand this idea that the root cause of the symmetry principle is the assumption that it is impossible to observe certain basic quantities which are called non-observable, and we will actually illustrate this fact by taking a proper example. Let us consider there is a system of two particles. As you can see in this figure, this 1 and 2, I have shown two dots here in the figure, and this two dots represents, let us consider, two interacting particles. These two particles are interacting with one another, and I have shown in this first figure that the position of the first particle with respect to an arbitrary origin O is R1, and that of the particle 2 is R2. You can see in this figure. Now, since these two particles are interacting with one another, so there will be an interaction energy, or you may call it a potential energy with respect to that interaction in this system. And we consider that this V is the interaction energy between these two particles 1 and 2 when the particle is at the position R1 and R2 with respect to the arbitrary origin O. Now, actually, the assumption that the absolute position is a non-observable means that we can arbitrarily choose the origin O from which these position vectors are drawn. The interaction energy should be independent of the origin, or in other words, you can say that the interaction energy V is invariant under an arbitrary space translation changing from O to O dash. You can see this figure. I have actually changed the origin from O to O dash. I have shown this in a separate figure here. And if you consider that the position vector of the first particle with respect to this another origin O prime is R1 plus D, and that of 2 is R2 plus D. It means R1 has been transformed to R1 plus D, and R2 has been transformed to R2 plus D. But the interaction energy between these two particles will not change on changing the origin. Why? Actually, the interaction energy V is a function of the distance between the two particles. And you can see from the first figure, when the position vector of particles 1 and 2 was R1 and R2, then the distance between these two particles is actually a mod of R1 minus R2. And even when we have selected the origin O prime, even in that condition you can see the separation between these two particles is again modulus of R1 minus R2. It means by changing the origin or changing the value of these position vectors, the separation between these two particles does not change. And this interaction energy V is only a function of the distance between these two particles. So I have mentioned here that this V is simply equal to V of mod of R1 minus R2. So if you want to measure the interaction energy, you have to measure the separation between the two particles. And R1, R2 will be not measured, or it cannot be measured because these position vectors are not absolute. When we simply change the origin, the position vector changes. So we simply say that the position vector R1 and R2 are non-observable. Okay. So in this example, the position vector is, or the position, you can simply say position of the particle is non-observable. And making a transformation of R1 to R1 plus D and R2 to R2 plus D does not make any difference in the value of the interaction energy. So this is just a translation of the position, or you can say just a translation of the space. Actually, this translation of a space leads to a very important symmetry, and this symmetry leads to a conservation principle which is called conservation of linear momentum. Okay. So what I have told you, I have told you that the absolute position is actually a non-observable because it depends on the selection of our origin, and the origin selection is arbitrary. So it is not measured in an experiment. Only to measure the interaction energy, we have to measure the difference of the position vectors, that is the distance or separation between the two particles. So you can say that the interaction energy is actually invariant under an arbitrary space translation of the origin from O to O dash. Okay. Now let us see. As you know from the Newton's second law of motion that rate of change in momentum of a system is equal to the force acting on the system. So this dp by dt, which represents the rate of change in momentum, that will be simply equal to vector f. And you know that this f, that is the force acting on the system, which is actually an internal force because this is interaction between the two particles. This force is simply equal to the negative gradient of the potential energy or the interaction energy. You know it. So F may be written as minus gradient of V, that is minus del V. And since there are two particles, so you can also write equivalently this expression as minus del 1 plus del 2V. Actually here del 1 represents the gradient operator for the first particle and del 2 for the second particle. You may write it equivalently. But as you can see from this equation number 1, see this equation 1. Since V is a function of R1 mod of R1 minus R2, it means V is not a function of R1. It is not a function of R1. It is independent of R1. Similarly, V is also not a function of R2. That is, it is independent of R2. And you know, when you use the operator gradient, that is del, that is simply the differentiation with respect to the position. But as our potential function V is independent of R1 and R2, so what will be this gradient of V? This gradient of V will be simply equal to 0 because because V is not a function of R1 and R2. So you can see that this dp by dt will be simply equal to 0. Okay. And if dp by dt is 0, you know P will be a constant. It means that the linear momentum of our system is conserved or constant. So what you have seen here, actually you can see that when we consider that the position is a non-observable, and that means if you change the position, that position does not make any difference in measuring the interaction energy, then the total momentum of our system remains conserved. So you can say that invariance of a space leads the conservation of linear momentum. Okay. So how invariance of a space leads to conservation of linear momentum, I hope you have understood it. Okay. Now I will actually give you some more examples without any proof. But lastly, we will see in this lecture how you can say that the charge is a conserved quantity and what is the invariance principle or the symmetry principle which leads to the conservation of charge. We will discuss it in very detail. But one thing you should remember that in this chapter, after this lecture, we will see separately the different conservation principle. This lecture is only meant to give an idea of conservation principle and the corresponding symmetry. So I will not explain each and every conservation principle. I will explain only one conservation principle, that is conservation of electric charge, in detail, and then we will see some information regarding the different conservation laws for that the conservation laws which is resulted from which symmetry. We will only give an information, but in the forthcoming lectures we will discuss each and every conservation principle in very detail. Okay, so now I am giving you some other examples, and that will be just as an just information, not a detailed explanation. Okay, you have seen in the first example that position is a non-observable, that is the absolute position cannot be measured, and so that is called a non-observable, and associated with that non-observable the symmetry was the translation of a space, and that leads actually the principle of conservation of linear momentum. In fact, in a similar manner, you can see that the absolute time is also a non-observable. Okay, absolute, you can't measure the absolute time, because always whenever an event takes place, we measure the time interval. Okay, measure the time interval. So absolute time is a non-observable. Okay, and if we actually make a translation in the absolute time, let us say the time t now it becomes t plus tau. This is just a translation of time. So this translation of time actually gives a conservation law which is called conservation of energy. So I have mentioned here that the physical law must be invariant under the time translation, which is given as t tends to t plus tau. Okay, so this invariance of time translation actually results in the principle of conservation of energy. Okay, now you know angular momentum is also a conserved quantity, and this conservation of angular momentum is corresponding to actually the symmetry associated with the spatial direction in space. So if you assume that the absolute spatial direction to be a non-observable, then we derive a rotation invariance, and this rotation invariance actually leads to the conservation principle of angular momentum. Okay, in a similar manner, if you consider that the absolute velocity or the uniform velocity is a non-observable. Okay, mark this. If we consider that absolute velocity is a non-observable, and absolute velocity is never measured, we always measure the relative velocity. So you can take absolute velocity as a non-observable quantity, and if you consider that absolute velocity is a non-observable, then actually the symmetry is related to the Lorentz invariance. Then the symmetry is Lorentz invariance, and this Lorentz invariance actually gives the conservation laws connected with the 6 generators of the Lorentz group. You know, Lorentz group has 6 generators. The page has been turned. This is a defect of my device, and it will be remedied very soon, so don't mind it. It will be just okay. So I was telling you that the Lorentz group has, you know, there are 6 generators, and when you consider that absolute velocity is a non-observable, then that symmetry actually leads the conservation laws corresponding to the 6 Lorentz groups. In fact, till now I have given some important examples of the conservation principle, like conservation of linear momentum, conservation of energy, conservation of angular momentum, and the conservation laws connected with the six generators of the Lorentz group. And corresponding to these laws, which quantities are non-observable, you have seen. Corresponding to the principle of conservation of linear momentum, you have seen that the absolute position is the non-observable. Okay. Corresponding to principle of conservation of energy, you have seen that absolute time is the non-observable. Corresponding to the principle of angular momentum, you have seen that the absolute direction in space is the non-observable. And corresponding to the conservation laws of the six generators of the Lorentz group, you have seen the absolute velocity or the uniform velocity is the non-observable. Actually, the symmetries or the invariants in all these conservation laws are actually associated with external symmetries. These are external symmetries. But particularly in the study of elementary particle, the conservation principle which we study are actually related not to the external symmetries, but they are related to the internal symmetries. Okay, they are related to the internal symmetries. So now we will actually see some of the important examples of the conservation laws and the associated symmetries and non-observable, where actually internal symmetries lie. Okay, and as I have told you earlier, that in this lecture we will only explain the principle of conservation of electric charge in detail, and then we will see just in a tabular form the informations regarding the non-observable, the symmetry operation, and the resulted conservation laws of some important conservation laws of used in physics. But as I have told you, in the forthcoming lecture, each and every conservation principle will be described in very detail. But in this lecture, our aim is to explain this fact by taking only one example, and that will be actually the conservation of electric charge. Okay? And I hope you have studied in your course on quantum mechanics the relativistic quantum mechanics, that is Dirac theory of relativistic quantum mechanics, and you have also studied in quantum mechanics, as I hope, the field quantization. And in field quantization, definitely you have studied the Lagrangian field theory. And when you say Lagrangian field theory, then we actually find a classical field equation. Okay? And that classical field equation actually when is written actually in terms of the Lagrangian density, and when we write the classical field equation in covariant form means in tensorial form, then what is that equation, or what will be the expression for the Lagrangian of the system? So according to the field quantization of classical field, the covariant form of Lagrangian of the system of a particle, what is the expression for that expression of Lagrangian? I will write here directly. If you have not studied field quantization, go through any standard book of quantum mechanics and study that chapter field quantization, where you will find the classical field equation, and also you will get the expression for the Lagrangian of a system. Okay. Now for this, let us consider an electron, and this electron is actually described by an array of complex fields, and this complex field is denoted by the symbol psi, and the Lagrangian, as I have told you, that according to the classical field theory of Lagrangian, the expression for the Lagrangian of this electron will be what? I have written it directly. So this is actually the expression for Lagrangian written in covariant form. So you have to remember it. The Lagrangian of this electron will be written as L equal to I over 2 psi star gamma mu del mu psi minus del mu psi star gamma mu psi minus m psi star psi. Actually here this psi star is the complex conjugate of psi, and in fact in this equation what are these gamma mu and del mu, you can see. Actually, if you have studied the relativistic quantum mechanics, that is Dirac theory, then you can see these quantities. Actually here this gamma mu is equal to minus I beta alpha mu, where alpha and beta you know are known as Dirac matrices, and in covariant form this del mu psi is simply equal to psi mu, where mu is actually integer, that is 1, 2, 3, 4 and so on. Okay. Now this form of taking this form of Lagrangian, you will see that the Lagrangian defined in this equation 2 is invariant under the phase transformation. When there will be a phase transformation, the Lagrangian will not change, and that phase transition is defined, the transformation in phase is defined by like this. This psi will be changed into e to the power I alpha psi, where actually alpha is a real constant. So if you know psi is equal to e to the power I alpha psi, then its complex conjugate psi star, what will be this? This will be e raised to the power minus I alpha psi star. Okay. Now, actually the family of phase transformation is denoted by this symbol u of alpha, which is e to the power I alpha. Actually this is the phase transformation operator, and this u alpha is actually the unitary abelian group. Okay, and this is known as u1 group. Okay. Now you know that any abelian group actually follows a particular property, that its product is commutative. So if u alpha is actually an abelian group, then it will follow the commutative law of multiplication, and so we can write that this u alpha 1 times u alpha 2 is equal to u alpha 2 times u alpha 1. Okay. Now one can think that the existence of the u1 invariance is just trivial, but it is not so. Actually, according to Noether's theorem, you can see that the existence of this invariance is not trivial, but it is due to the existence of conserved current. If the current will be conserved, then only this invariance will valid. Okay. Now, how you can say that the invariance of this u1 abelian group is not trivial? It implies that that there is a conserved current. Actually, to explain this fact, we can simply study the invariance of the Lagrangian under the infinitesimal u1 transformation. So if you make the infinitesimal u1 transformation, what you will do? In fact, we will simply see, we can simply do that psi will be changed to 1 plus I alpha psi. Okay. So when this transformation will made, and you say that Lagrangian does not change, it remains invariant, it means the change in Lagrangian, that is delta L, will be equal to 0. Now you can see the expression for the Lagrangian here. I have written it in this equation 2. So taking the expression for Lagrangian L defined in this equation 2, now we will find the change in L, that is delta L. But as the Lagrangian will remain invariant, so delta L will be 0. So see this expression seriously and take and find the value of delta L by following the rules of partial differentiation. So you can see if we make the change in delta L following the rule of partial differentiation by taking the expression which I have defined in that equation 2, you can see what will be your result. I am not turning the page. You can see this will be in fact del L by del psi delta psi plus del L by del mu psi times delta del mu psi. This is just product of function plus del psi star del L by del psi star plus delta del mu psi star times del L by del mu psi star, and that will be equal to 0. Okay, this you can do it. This is just a simple differentiation by taking the rule of partial differentiation. Now you can write this expression like this. This is del L by del psi I alpha psi plus del L by del mu psi times I alpha del mu psi plus so on equal to 0. Now you can see when we will take actually this I alpha as a common factor, then this expression will be I alpha del L by del psi minus del mu del L by del mu del psi plus I alpha del mu, and this is del L by del mu psi times psi, and that equal to 0. Now actually the expression inside this square bracket, see the form of this expression. Actually this is just the form of Euler-Lagrange equation. You have definitely studied this Euler-Lagrange equation in your course on classical mechanics, and actually this term inside the square bracket is equal to 0 because this is just Euler-Lagrange equation. So if you write this Euler-Lagrange equation in covariant form, this bracketed term, you can write del x mu del L by del psi by del x mu minus del L by del psi equal to 0. In fact, this is nothing. This is simply the square bracketed term. Why? Here I have taken del x mu, and here is also del x mu. So this del x mu will cancel out, and your result will be just same as the term inside the square bracket. So you can take that this term inside the square bracket is 0, and so this equation which I have written here in equation 6, this equation actually reduced to the form of an equation for which the current remains conserved, and that conserved quantity will be written as del mu j mu is equal to 0. Del mu j mu equal to 0. Actually here this j mu is actually the current 4 vector, you know, and if this equation holds, actually this equation refers that charge which is actually the 0th order moment of the current. So you can write the total charge Q is simply equal to the 0th order moment of the current, and so Q can be written as integral J0 d3x. Okay, and as this current is conserved, So this equation actually refers that the total charge q, which is just equal to the zeroth order moment of the current, will be also a conserved quantity, and this conservation is due to the u1 phase invariance. So what you have seen here, actually we can see that actually charge is a conserved quantity, and this conservation is corresponding to the invariance of u1 phase invariance. Okay, so finally we arrive at the mathematical expression that relates the existence of conserved charges q and the existence of the symmetries. Okay, now just like charge, which actually remains conserved, and corresponding to this conservation principle, you know, the transformation was of phase and the symmetry was of phase symmetry. Okay, now we will give just an information in a tabular form for the important conservation laws of physics, and three things we will actually discuss here. Uh, the first thing will be what is the non-observable associated with that conservation principle. What is the symmetry transformation or symmetry operation in that case, and what conservation principle or law is actually corresponding to that symmetry transformation. We will see these three facts here. This is just an information, you should remember it. But as I have told you earlier, that every conservation principle related to the study of elementary particle we will see in the forthcoming lecture in very detail. Okay, but this table will give you just an information and you may remember it. This will be actually very useful for the objective type question asked in different competitive examinations, where you find such questions which is invariably asked in your examination. So let us see. The first example is difference between identical particles. This is a non-observable, and for this the symmetry operation is permutation. Okay, and the conservation principle which is actually followed by this symmetry transformation are Bose-Einstein and Fermi-Dirac statistics. Okay, next example is absolute space position. This is the non-observable, and for in this case actually the symmetry transformation is space translation, which is given as r is translated to r plus d, and by this you have seen that linear momentum conservation principle is resulted. Okay, next is the non-observable absolute time, and for this time translation is the symmetry transformation, which means t is transformed to t plus tau, and this leads to the conservation principle of energy. Okay, next non-observable is absolute spatial direction, and here actually the symmetry transformation is the rotation, and this rotation is mathematically expressed as r hat, which is actually a unit vector in a particular direction, is now rotated to another direction which is actually r hat prime, and this actually leads to the conservation principle of angular momentum. Now the next non-observable is absolute right or absolute left. It means this will be just a mirror reflection. R is changed to minus R. This is symmetry transformation, and this actually leads to conservation of parity. Okay. Now absolute sign of electric charge. You know actually the electric charge is of two types, positive and negative. So if there will be just a transformation of positive charge into negative charge, it may be possible because the sign of charge is actually a convention. If you say that the charge of electron is positive, that will be right. But only when you say that the charge of proton is negative, then it will be correct. So if there is a transformation of positive charge into negative charge, or in terms of the wave function, if you say that psi is changed to e to the power I alpha psi dagger, okay, then this transformation, this symmetry transformation actually leads the principle of conservation of charge conjugation. Okay, some more examples we will also see here. You can see that if the relative phase difference between states of different charges q is taken as the non-observable, then the symmetry transformation is given as psi transformed to e to the power iq theta psi. And this symmetry transformation leads to the conservation principle of charge. Okay. Similarly, the relative phase between states of different baryon number b, this is corresponding to the symmetry transformation psi to e to the power I b theta psi. Okay, b is baryon number, and this leads to the conservation of baryon number. The next is a relative phase difference between states of different lepton number L, and this symmetry transformation is defined by psi transformed to e to the power IL theta psi, and this gives actually the conservation law of lepton number. Okay, and the last example I have written here is difference between different coherent mixture of p and n states, proton and neutron states. That is, for this non-observable, the symmetry transformation is defined as p over n transformed to u p by n. Here u is actually represents the up quark. Okay, and this actually leads to the conservation principle of isospin. So in this table you can see up to this example, absolute spatial direction, that is the principle of conservation of this Bose-Einstein and Fermi-Dirac statistics, linear momentum, energy, angular momentum. Actually the symmetries are external, but after that in every example there is actually the internal symmetry, and this internal symmetry also correspond to a particular conservation law. So I hope you have understand finally that every conservation law is corresponding to some symmetry transformation, or and to every symmetry transformation is defined for some particular physical quantity which cannot be observed, and that is called non-observable. So actually the non-observable and symmetry transformation is the root cause of any conservation law. In this lecture I have actually explained only one conservation law in detail, that was conservation of charge. But as I have told you that in the forthcoming lecture we will see the important conservation laws with a proper example and in very detail with proper calculation. I hope you have enjoyed this lecture. This is very important. Go through the video seriously. Write down each and every points in your notebook. Definitely, then you will be able to write the answer of questions of your examination, and that examination may be a university examination or a competitive examination.